Mr. B. Dhanasekar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. We are seeing the subject that is theory of computation. Let me start with the previous CAP, that is the lecture whatever we have seen in the previous lecture. Given a deterministic finite automata, how do you find out the regular expression described by the finite automata? In fact, both finite automata as well as the regular expression are used for describing a class of language called regular languages, but their representations are different. One looks like the expressions and another one looks like transition diagrams. So, given the description of a regular language in the form of a finite automata, how do you find out the equivalent, that is regular expression from that? That is what we have seen as far as the previous lecture is concerned. So, today we are going to have, that is the comparison in between the regular languages and non-regular languages. If I am saying that there is a regular language which comes under the class of the Chomsky hierarchy, there are other languages also available as far as the Chomsky hierarchy is concerned. So, what is the place where we are having your regular language? And suppose if you find that the language is not regular, how do you prove the language is not regular? That is the question. So, if the language is regular, then we will not be able to construct any deterministic finite automata for that, or we will not be able to find out there is an equivalent regular expression, or we will not be able to find out any non-deterministic finite automata. In fact, if you find that for a language, if there is no equivalent finite automata or regular expression, then the language is going to be a non-regular language. To prove some language is regular, then it is very simple. You just go and construct the equivalent finite automata. But whereas, if you want to prove that some language is not regular, then it is not so easy. So, we will go for a tool called the pumping lemma. So, the pumping lemma can be used for proving some language that is not regular. So, let us see that is what is a regular language in this lecture. Then we shall see that is what are the, there are some examples for non-regular languages. Then we shall see how we are defining the pumping lemma and how it is used for proving the non-regular languages with the help of the pumping lemma. As far as the definition component is concerned, we have that is the most restricted language as far as your class of Chomsky hierarchy is concerned. That is the simplest and most restricted in the norms Chomsky hierarchy. That is about your regular language. And another important property here we have to understand is every finite language is going to be a regular language. It is because of, so first you should understand what is a finite language. A set in which we will be having only finite number of strings. If you are having finite number of strings, then for every string it is possible to construct a finite automata. A string is said to be finite if in the there is your given finite automata, every state will be visited at most once. So, whatever be the size of the string and whatever be the number of strings we are having, it is possible to construct finite automata. If we can construct finite automata, then the language comes under automatically regular language. So, whatever be the number of strings, that is if you are finding the language is going to be a finite language, then the language will definitely be a regular language. And the next one is it could be generated by any finite automata. So, having a finite automata, definitely we can say that the language is going to be a regular language. And another thing, that is what we want to have as far as this current topic is concerned, that is not every language is regular. So, there are languages which are considered as non-regular languages. So, now the question is some examples like what are the classes of languages which are coming under non-regular class. So, we have few examples here. The first one is set of palindromes. So, here you can see that the strings which are of the form something like W reverse. a string which reads same both from left to right as well as from right to left. They are called the palindromes. Another one, set of all arithmetic expressions. So, that is also going to be a class of string, that is class of language which could not be generated with the help of a regular expression or with the help of a finite automata. Then a very simple one, the set of all balance parentheses. For every opening bracket followed by that there should be a closing bracket. It is not a closing bracket followed by a opening bracket. So, we can have a opening bracket followed by that we can have a closing bracket, even any number of nestings. So, it looks like very simple language, but certainly it is not possible to recognize these kind of languages with the help of any regular expression or with the help of finite automata. Another one is a very simple, that is string of the form, that is 0 power n followed by 1 power n. So, we have seen something like 4 or 5 number of languages which are considered as non-regular languages. In all these languages, we have to understand that there is a need for remembering what we have recognized so far and what is yet to be recognized. So, without understanding what we have recognized so far, it is certainly not possible to recognize the remaining part. Let us consider the first string, that is palindrome. The first part of the string we must remember in order to recognize or understand the reverse of the first part as the second part of the string. So, without remembering what is the first part of the string, certainly it is not possible to remember the second part of the or recognize the second part of the string. Or even if it is going to be something like the set of all balance parentheses, first of all we should understand how many opening brackets so far we have recognized. So, without knowing how many opening brackets we have recognized, we can't recognize equal number of closing brackets. It can be either that is opening bracket immediately followed by closing bracket, or opening bracket any number of times followed by the same number of closing brackets. So, we must know how many opening brackets so far recognized, or we can remember the string that is 0 power n followed by 1 power n. The number of zeros recognized should be same as the number of ones recognized in the string in the same order. So, all these need some amount of memory in order to recognize the complete string. As far as any finite automata is concerned, the memory is very limited. Just by sitting a state, we will be able to understand what is the previous symbol or what is the most recently recognized symbol. That too, in some cases it is very difficult to understand what is the previous symbol we have recognized. So, it is certainly not possible to remember the complete pattern we have recognized so far or up to this point. It is only because of the memory problem with the finite automata. But this could be simply that is overcome by having another type of automata called push down automata. The main difference in between the push down automata and the finite automata is the existence of a stack in the push down automata. So, when we have a stack, theoretically it is going to be infinite amount of the size or infinite number of symbols we could store inside a stack. With the help of that, we can remember any amount of information. So, that is the reason why it is possible to recognize these strings like palindromes or balance brackets or even 0 power n followed by 1 power n. These set of strings could be very easily recognized provided if you go for a push down automata. The push down automata is a recognizer for context free languages, that is coming under the next class of the languages in the Chomsky hierarchy. So, a regular language is always going to be a context free language, but whereas in the case of a context free language, it need not always be a regular language. Regular language is a subset of the context free language, but the reverse is not so. So, a language which is not a regular may be a context free language, but we should know whether it is going to be regular or not regular. If you are asked to prove that some language is regular, you are forced to generate a deterministic finite automata, or you are forced to give an equivalent regular expression for the same language. In some cases, we may not be able to do that. So, we will go for the pumping lemma that could be used for recognizing or proving that the language is not going to be a regular language. So, here is the pumping lemma we are having. So, first we are having an automata. So, the pumping lemma proof is completely based on proof by contradiction. So, proof by contradiction means if you are given a string some w or if you are given a language that is L, first of all we will assume that it is going to be a regular language, and if it is regular, then there will be a finite automata like this for that language. And now we have to find out that there is a string in the language which may not be in the language, or there is a string in the language which may not be recognized by this finite automata. But usually we will follow the first approach. we will find a string from this, but it may not be available in your language that is given as L. So, that is what here we have to do. So, we will start with the language that is L, assume that there exists a finite automata and prove that a string accepted with this finite automata which is not there in the language. If you want to claim that the finite automata in question is the automata for the language, only if the language of the finite automata should be same as the language whatever is given in question. So, here we have an automata that is with the P naught as the starting state and the P n is going to be the final state, and we find that there is an intermediate state that is P I, and the string recognized. Suppose if I am making a path from that is P 0 to P I and then finally to P n without repeating a state, then the number of states or the number of strings to be recognized in this manner is going to be finite only. Sometimes we may have a path directly from P 0 to that is P n with some label, maybe some B 1, B 2, B 3 etc. up to some B m, that may be a string of finite nature, and here we are having another string that is P 0 to that is P I, then P I to P n, it is also going to have that is m number of symbols, but sometimes we can take the path that is from P I to P I back with the labels available on the path as A I plus 1, A I plus 2 etc. up to A j. The very important thing here we have to understand is the path from P I back to P I could be taken any number of times. So, we can visit this any number of times means the number of strings produced by this path, that is from P 0 to P I back to P I any number of times to P I and then finally to P n is going to be infinite in nature. So, now we have to find out an automata in which there may be infinite number of strings possible. We have already seen that if the language is going to be finite, it need not be proved as regular language, because it is by definition itself every finite language is going to be regular. But whereas in the case of a language, if you are having with the infinite number of strings, then there is a possibility that the language may be a irregular language or a non-regular language. So, those kind of languages here we have to consider. So, now here is the lemma. First we are taking a string that is language that is L and we assume it is going to be a regular set. It can be either considered as a regular set or it is going to be a regular language. The condition is every string that is W in that is L, that is the condition here for W is W must be greater than or equal to n. So, here is an important point which we have to understand, the reason, that is why we are taking the length of the string W greater than or equal to n. Suppose if you are taking a string that is W whose length is less than n, then there is no need of visiting a state more than once. So, if you take a string like that, then definitely the language is going to be finite, and finite languages are going to be always regular languages. So, we must select a string in such a way that at least one of the state will be visited more than once. If you want to ensure that a state is visited more than once at least, in that case the number of symbols available in the string must be either equal to the number of states available in the finite automata equivalent for that, or the number of symbols available in the string must be greater than the number of states available in the finite automata which is designed for recognizing the same language. So, that is the reason why we are having the constraint, that is your W must be, or the length of W must be greater than or equal to n. So, select a string whose length is greater than or equal to n, where n is the number of states available in the deterministic finite automata which is assumed to be existing for the language L. So, now we have to go for splitting the string, that is W, into 3 components. That is, we have already seen an automata where we have a state called P 0, an intermediate state that is P I, and another one is going to be that is P n, that is the last state of your finite automata. The strings how we are dividing, the first part is from P 0 to P I, that is the first part of the string, and the second part of the string is the string which is traversed or which is visited by taking the path from P I to P I. Then the next step is the third part of the string. The third part of the string is you start from P I and go to P n, that is the last state of your finite automata. As far as the first part and the third part are concerned, we will not repeat, but whereas in the case of second part, it could be taken any number of times including 0 times. So, if it is 0 times, then the resulting string is simply the concatenation of the first part and the third part, and if it is one time, the resulting string is going to be the first part followed by the second part followed by the third part, but the second part could be visited any number of times. So, that is the idea behind the selection of the string and splitting that string into 3 components by the pumping lemma. It is going to be x, y, z. So, just you take the string, divide it into 3 components x, y, z, and then you just apply the pumping lemma to ensure that the string is going to be there in the language of the automata. If you find that the language is or the string is not going to be language of the automata, then we can simply go for declaring the language is not going to be a regular language. I will go for a break, and after a short break we will continue the lecture. Welcome back. We are seeing the pumping lemma, which is meant for the regular languages, that is used for proving the language is not going to be a regular language. So, here is a definition for that. We are selecting a string that is w and whose length is going to be greater than or equal to n, where n is going to be the number of states available in the automata assumed to be existing. Now, we can divide this w into 3 components. It is x, y, z, such that the first condition, the string that is middle string, that is your y, should not be equal to epsilon. If I take this y as epsilon, then visiting this y any number of times does not make any difference in terms of the string to be recognized. That is your string which we are considering, that is your x, y, when it becomes epsilon, visit this y any number of times, but that does not make any difference. Finally, we will get only x z. So, we are having a condition that this y should not be equal to epsilon, and the second condition, the length of x, y, that is the first 2 components, must be less than or equal to n. So, what kind of constraint it is posing here is, the string which you are taking for y should be possibly from the beginning of the word string, that is x, y, z. We should not go for the other end of the string for selecting the string which we have to repeat. The pattern to be selected for repetition must be from the beginning of the string. So, that is why we are having x, y less than or equal to n. So, now if you find that x, y, z is going to be a split for this w with all these conditions are satisfied, your y is not equal to epsilon and the length of x, y is less than or equal to n, then the very important thing which you have to prove here is, you just push this or pump this y any number of times. That is what for all k greater than or equal to 0, that is we are going to pump this y k number of times including 0 times. So, for every value of k, if the pumping yields a string which is there in L, then we can claim that the set of all strings w are going to be regular. But if you find for at least some k, at least for one value of k, if the resulting string, that is x, y to the power k z is not going to be in L, then immediately we can say that the language is not going to be a regular language. It is because of, we assume that L is a regular set, and if it is regular, there exists a finite automata. We have taken a string that is w with a repetition factor that is going to be f y. Then if it is going to be repeated any number of times, whatever be the number of times we are repeating, the resulting string must be there in the language of the automata. And if it is not satisfying that condition, then either the regular language, that is your L, is not going to be regular language, or we can say that there is no equivalent finite automata. So, this is how we are going to prove as far as our pumping lemma is concerned. We can take any number of examples as far as this particular part is concerned. You take a language, there is a regular expression, or can be a pattern, or it can even be in a descriptive nature, and if the question is like just to show that this is not going to be a regular language, then straight away we can select the pumping lemma for proving the language is not regular. Sometimes it is required to find out whether the language is regular or not. If you want to find out whether it is regular or not, first of all you try to find out whether it is possible to construct an equivalent finite automata or construct an equivalent regular expression for describing the language or not. So, if you succeed in finding the regular expression or finding the equivalent finite automata, then we can simply declare this language as regular language. But if not, we have to prove the language is not regular. For proving the language not regular, the only solution is we have to go for the pumping lemma. So, here we have one simple example. See the language, that is your L is going to be 0 power I square such that I greater than or equal to 1, and we have to prove that it is going to be a not regular language. First, you should understand what this language is. It is 0 power I square, that is I takes the value from 1 to anything, it is infinite number of times. So, when you take the value of I is equal to 1, it is 2 number of zeros. When I is 2, it is going to be 4 number of zeros. When I is 3, then it is going to be 9 number of zeros. So, the number of zeros, that is strings with perfect square number of zeros, is going to be the part of the language. So, L contains the set of all strings with perfect square number of zeros. So, by pumping lemma, what we should understand is, first you assume this language is going to be a regular language, then you select a string, that is W, and the condition there is the W must be in the language accepted by this automata. So, we have to select a string W such that W is there in the language. Another condition is the length of the string, that is W, must be greater than or equal to n. It is because of we should be able to find out a pattern from this W which will be repeated as many times as we want. So, now we can go for writing this W as the x y z. So, here we find that the condition, first one, it is going to be y should not be equal to empty. It means the length of your y must be at least 1. So, now we can go for pumping this y k number of times. So, first you should understand what is this string, that is W's length. So, the W's length is going to be depending upon how many times we are pumping this y. Suppose if I am pumping this y exactly once, it should be a string in the language of the automata, that is the first condition, and if it is a string available in the language of the automata, then we should be understanding that the length of the string is going to be a perfect square. So, x y z, that is its number of zeros available in x y z must be either that is 2 or 4 or 9, or in general the number of symbols available in your x y z is exactly equal to n square. It is because of our assumption that your W is greater than or equal to n. So, now the question is, we go for pumping. So, the pattern to be pumped here is y, that is y is the pattern which we are going to pump. How many times you are going to pump is exactly one more time than the number of times already it is pumped. Already it is pumped once, which is giving you the string of the length, that is n square. Now, we are going for pumping one more time. So, here we have to understand what is the length of this W which we are pumping. The length of the W is, sorry, length of y is going to be exactly a number in between 1 and n. So, now what is the maximum size of the increase in the length of your x y square z? So, the taken string is going to be x y z whose length is n square. Now, we go for one more time pumping of this y, that is giving a string, that is x y square z, and when it is pumped, there is one more time, that is y is pumped one more time, the length may increase by at most, that is n, but it is not exactly n, it is at most by n. So, it is a number in between n square and n square plus n, and it is very important that we can understand this n square plus n is going to be a number less than n plus 1 the whole square. If x y square z is a string there in the given language, that is L, then the length of the string, that is x y square z, must be the next length which is accepted by this automata, that is nothing but n plus 1 square. So, the length of the string can, if it is n square, the immediate next string must be of length n plus 1 square, the next one must be n plus 2 square. That is the meaning of the language which is given for us. But here we find that the length of the string, that is which you have taken, that is x y z, is exactly n square, but after the next pumping we are getting a string whose length is less than n plus 1 square. So, the length of x y square z is not going to be a perfect square. So, if it is exactly lying as or exactly n plus 1 square, this x y z y square z may be a string available in the language, but here you find the length of x y square z is exactly in between n square and n plus 1 square. So, that will give you the conclusion that W is not going to be in the language, that is L. We started with the assumption that W, sorry, the length, that is your W which you are taken from the language is there in the, that is accepted by this finite automata, but here we find that your W, after pumping this y twice, we get a string whose length is in between n square and n plus 1 square. It is neither n square nor n plus 1 square. So, that is contradicting our assumption that the string is going to be in the language, or it is going to be accepted by this finite automata. So, we can conclude that the set of all strings whose length are perfect square is not going to be a regular language. So, first you start with the language, assume that it is regular, and you say that it is going to have a finite automata, select a string which is going to have at least one more, that is a state is visited more than once, then split it, then pump it, find a value for k. So, if you are finding some value for k, so that the string is not there in the language, immediately you can say that the language is not going to be a regular language. See, one more example here we have, that is L is u, where u belongs to 0 or 1 star. So, it is going to be something like one pattern u, you take it one more times. So, 2 times the same pattern. Now, the question is, can we have this kind of strings with the help of recognizing either with the help of your regular expressions or with the help of finite automata. The same story here also we have to repeat. We assume the language is going to be regular first of all, and then take a string, that is you are having your u is 0 power n followed by 1. When u is 0 power 1 n followed by 1, your w becomes 0 power n 1, 0 power n 1, and we can understand the length of the string, that is w is going to be 2 n plus 2, which is satisfying the condition, that is your n, that is nothing but the length, sorry, the number of states available in the finite automata which we have assumed as existing, and w could be decomposed into, that is x y z, and now you can very easily, that you can take so many number of cases. So, you take the first part, that is 0 power n followed by 1, then followed by 0 power n followed by 1. Suppose if you take, that is your y which contains exactly, that is some number of zeros, maybe it is k number of zeros. So, what will happen here is, you go for pumping y 0 number of times. If you go for pumping this y 0 number of times, this string will be reduced to 0 power n minus k followed by a 1 followed by, once again this is going to be the same thing which is not going to be repeated without any modification. So, the resulting string is going to be 0 power n minus k 1 0 power n followed by 1. And we understand that the value of n is going to be, that your k is going to be, or the string, that is your y is not going to be empty. If y is not empty, the number of zeros available in the first part will never be matching with the number of zeros available in the second part. So, automatically we find a string which is not of the form u u. So, that gives you the contradiction that we have an automata for the language, that is u u. So, this is how we are proving the languages as not regular. So, let us summarize. So, we started with what is a non-regular language, and what is going to be the role of the pumping lemma in proving the languages as not regular, and how the pumping lemma is used for that is the proving the languages not regular. So, we are having actually the pumping lemma for both regular languages as well as for context free languages, and here we have seen only the regular, that is pumping lemma for regular languages. And there may be large number of problems as far as this case is concerned. You may be given, that is any number of that is languages, or any language may be given us, which may be used, that is which may be, that is you are asked to prove the language is not regular. Here we have some of the problems. We have, that is a power n followed by b power n, number of a's and number of b's are same. Here it is number of a's is going to be less than the number of b's. So, that is one condition. Another one is the set of all palindromes. We are having w reverse, and another one here we are having, that is x, where the number of a's and number of b's are going to be same. Then here also the number of a's, and it is going to be number of, that is a's here, total number of a's must be equal to the number of a's as far as the third part of your string is concerned. These are the problems which could be, that is proved as not regular with the help of the pumping lemma. So, you just understand what the pumping lemma is and prove the problems as, and that is your not regular languages. So, with this I conclude this lecture. Thank you all.